Welcome to this video on the force versus time graphs. In this video, we're going to be taking a look at how we can put together all the information that we were talking about in the last video, which was momentum as a rate of change of momentum. It's just also a neat way to put everything in kinematics together into a nice package. So let's start with just a little example. Let's say we have a little box and it's sitting on a surface. So we're going to draw a free body diagram for it to begin with. So we have weight and normal force. And let's say something's applying a force to it, which is larger than the amount of kinetic friction that it's experiencing. Now these are not drawn to scale, but I'm using these little tick marks just to show you the difference, that one force is longer than the other. So if I was to write out a net force equation here, a force summation, I could say the force applied minus the force of kinetic friction is not going to be equal to 0 because one of them is bigger than the other. And for argument's sake, let's just say it's equal to 4 newtons. Now let's say all of a sudden you decrease your push and you match whatever the friction is. So now the force applied has shrunk a little bit and it's going to match the force of kinetic friction. Okay, if I was to rewrite my force summation or my net force equation here, I should see that these would come out to a net force of 0. So that's stuff that we talked about quite a lot before. If I were to describe in words what's happening from the one scenario moving into the next, I could say that, well, I have a net force that's not 0, so this means that this object is accelerating to begin with. And then at some point, once you decrease your applied force, your net force becomes 0, and that means now that I'm moving at a constant velocity. So far, just kind of a little bit of review. If I then ask you to graph the object's velocity versus time, what we could say is, well, for the first segment, we don't know how long this is happening for, but for the first segment, we need to show that the object is accelerating, and specifically, it's getting faster here. And then at some point, it reaches a point where it hits constant velocity, and that would be just this horizontal line. So we have some time passing where the object's getting faster and faster because we have an unbalanced force, and then eventually it becomes a constant velocity, which means a horizontal line. Now, adding in the new content that we've been discussing, which was the momentum versus time, if I wanted to take this velocity versus time graph and change it into a momentum versus time graph, it's actually pretty easy because we know that momentum is mass times velocity. So essentially what I could do is I could take the velocity at any given second here and I could multiply it by the mass. Well, I didn't give you a mass for this, but we could come up with mass value and then multiply each of these velocity values by the particular mass value. Now you can think of that if, let's just say for example, that the mass was equal to 2 kilograms, which in this example it's not necessarily going to match up with the numbers, but we'll take a look there. 2 kilograms, and let's say the first velocity increment that I have here is just 1. Well, 2 times 1 gives me 2 kilogram meters per second. Now, that means that wherever there was 1 lined up here with the x-axis, it's not going to line up to 2. So all that would happen is that this graph would look exactly the same. It would just be steeper, reach a higher point, and then level out. Because just like we said before, in this portion it's accelerating, and in this portion it's at a constant velocity. That would match this, right? Here the momentum is increasing, and here the momentum is constant, because whatever the velocity is, that's what the momentum is in the situations we deal with where the mass isn't changing. Now there's one more step that we want to take that takes this to even more useful level, and that is to try to make a force, really net force versus time graph. And we know that net force has 2 different possible ways we can find it. It's mass times acceleration, but now we saw from the last video that it can also be the change in momentum divided by time. So there's two ways we can look at this. If we wanted to plot what was the force pushing on the object for various time intervals, we could go back to our free body diagrams and we could say that the net force was 4 and stayed 4 and then it became 0. And that's pretty easy, right? Because I could just say 1, 2, 3, 4. Let's say the net force here is 4. It stayed 4 to begin with, and then it jumped down to 0. And what we would see there is that this would be the net force versus time graph for this velocity graph or this momentum graph. But there's one more connection that we can make that makes this actually really neat. If we wanted to sketch the graphs without knowing this information that's down here about the net force equations, what we could do is one of two different things. Because we know that net force is the rate of change of momentum, that's like saying on a momentum versus time graph, so on a P versus T graph, the slope should tell me the net force, because the change in the momentum divided by the change in the time, which is how you would find the slope from this graph in the middle here, that would tell you the net force. So what's kind of neat is that the slope of this portion of the graph is the net force for the first segment, so that should be equal to 4 based on the example number I gave. And then the net force for the second section is just 0. And that works out pretty nicely, and it matches up what would be here. This value would be 4, this value would be 0 in terms of net force. One alternative way that you can even look at this, and this is what makes this so neat where everything kind of comes together, is you could take your velocity versus time graph and say that the slope of a velocity versus time graph tells me the acceleration. So for this first segment over here, if I was to get the acceleration, let's say the acceleration was equal to 2 meters per second. And then over here, because the slope is 0, the acceleration is equal to 0 meters per second. Sorry, and that should be a squared. That if, like I did to get the momentum versus time graph, where I multiplied all the velocities by m, I could even take the slope now and just multiply the slope or the acceleration by m, and that would give me the new slope of this graph. And it all kind of ties together, because if I have a velocity versus time graph where the slope is equal to a, if I multiply the a values by m, as we see here, I get net force. Or I can use the slope of the momentum versus time graph and I could get the net force. So there's multiple ways to kind of put it together. The last example that I'm going to do here is where we're going to kind of work backwards and see one final cool thing that we can use to solve these kinds of problems. Say I start with a net force versus time graph. So I give you some information. Let's say the information I give you is, well, let's switch it around a little bit. Let's say that it's 0 to begin with. And we'll say that it's going to step up like this. And then finally we'll make it step up one more time. Okay, so if I were trying to read this graph, a couple different things that I could pull from the graph. I could say that for the first, let's say it's just 2 seconds here. For the first 2 seconds, we can see that the net force is 0. For the next 2 seconds, let's say that the net force jumps up to, say, 4. And then for the final 2 seconds, we'll say that the net force jumps up to 8. Okay, so let's just think about from a free body diagram perspective, or balanced forces, what's happening for each segment. For this segment, the net force is clearly 0, which means the object's at a constant velocity or it's at rest, either one, depending on the context of the problem. For this next segment here, if it has a net force of 4, that means that the object is accelerating, right? And if we knew the mass, we could solve for what its acceleration was. For this segment over here, what we're saying is the net force is equal to 8. So now it would be accelerating even more because it has even more of a push on it. Now the cool thing is that if you find the area underneath one of these segments over here, or I could find the area under this segment over here, let me just do that in a different color so that we can see the difference here. What that would tell us is the change in the momentum or the impulse, which is kind of cool. So for each of these things here, I said it's going to take 2 seconds. So that's 2, 4, and then this would be 6. So for this first segment over here, if I find this area underneath, it's clearly 0, which means that the momentum is not changing at all, which matches up with what we said over here. Another way again to write that is that the impulse is 0. For this middle section, we'll go ahead and switch out our color again so we can see it. For this middle section over here, what we're essentially saying is that the change in the momentum would be the area under this line, so that's 4 times 2, because we have a time change of 2 and a force value of 4. So 4 times 2, that's going to give us 8. So our change in momentum is 8 kilograms meters per second. It's also our impulse, right? And then this final section over here, where we have a net force of 8 and it's still moving for 2 seconds, that would be 8 times 2, which is 16 kilogram meters per second. So that means that we can tell how much our momentum is changing by the net force equation, or the net force graph versus time. So if we were to write this out in an equation form, we know that we wrote that net force was equal to change in momentum over change in time. This could then be multiplied by the time on each side, as we can see here. And that shows us that the net force times however long that net force is acting for would tell us the change in the momentum, or the alternative way is called the impulse, which is kind of cool. So what we can do here is, by finding the area of a net force versus time graph, we are essentially finding the change in the momentum of the object. Now you could go and you could actually graph those back on the previous 2 graphs, but for the sake of this video already being a little long, we're going to skip over that. So I hope that helps. Try some practice problems and let me know if you have any questions.